All right, what we're going to do now is take a look at the hydrostatic force on a dam that we talked about in class. Here we have a cross-section of, say, a canal or a river that can be described by this particular function based on maybe data that you collected at different depths at different locations across the river. And the maximum depth is about 18.2 meters. So that's what we have going on in this sketch. The idea here is we would like to figure, if we're going to put a dam over it, how much total pressure or how much total force is going to be pushing against this dam. Here's the problem. We got a couple scenarios here where, let me get a different color, where we have, for example, at locations of different depth, we've got different pressures. So for example, I'm going to have less pressure up here at the top of the water level than I am down below. It's going to increase as I go. So I've got a dynamically changing pressure. Now, if I look at a thin strip, for the most part, the pressure here pushing against it everywhere, it's not exactly the same pressure because there's a slightly greater pressure here at the bottom compared to the top of the strip. But as I make these strips really, really thin, for all practical purposes, we can assume a constant pressure across the entire strip. So we're going to use the fact that pressure is force per unit area, which is really saying that force is pressure times area. So what we need to do is we need to come up with a pressure reading at a given depth, and we need to be able to figure out what the area of this strip is so that we know how much force is being exerted there. So a couple things we need to do. Here, if I figure that as my x-coordinate, you'll notice that because this function is symmetric about the y-axis, we do have some symmetry that we've got going on here. So the distance from here to here is really going to be twice x. Now, the distance vertically of this rectangular strip is going to be delta y. Eventually, when we take the limit of this, we're going to call that dy. Because it's calculus, we take the limit, we'll be able to create an integral. That's our goal here. So, if I want to find my little forces, force sub I, I'm going to look at my little pressure sub i's times my area sub i's. So I'm going to need a pressure as a function of, say, depth, or in this case, what I ideally would like would be as a function of the position y. And then we also would like the area as a function of y. Notice that we can calculate the area by saying this is 2x. That's delta y, so it's going to be the product of those two things. But here we're slicing it with respect to y, so what we really need to do is we really need to be able to convert those x's into y's. Well, the nice thing about that is the x-coordinate at this location, I can relate the x and y coordinate by this expression. So this now gives me a way to solve for x in terms of y. So we can do that really quickly here. I'm going to say that I'm going to divide both sides by this number, and then I'm going to take the fourth root. So x to the fourth is going to be y divided by 0.000111375. So x is going to be the fourth root of y divided by 0.000111375. Okay. So that's our x-coordinate. So we need twice that because we want to go from here to here. And then we need to multiply that by delta y. So the area is going to end up being 2 times the fourth root of y over this mess, 0.000111375, times delta y. So there's the area. So now what we need to do is we now need to find a relationship between pressure and y, or as we collected the data, pressure and depth. But we can also realize that if I take the depth d that if I take d and y and add them together, I get the total distance from here to here, which is 18.2. So I can use the fact that d plus y equals 18.2, or in other words, d is 18.2 minus y. Okay, so we're going to eventually use that because we're going to create a pressure function. We're going to create pressure as a function of d, and then we're going to write it as pressure as a function of 18.2 minus y. We'll let the computer algebra system basically do that for us. We'll define it p as a function of d, but then we'll just substitute in p of this expression, and the CAS will handle all the grunt work for us. Okay, so in order to do that, we really need the data. So if you recall, we collected the data. Sorry, put my glasses on here. And the data looks something like this. Your data may slightly vary, but it was a nice linear fit. Now, within the DataMate app, or I'm sorry, the DataQuest app, we could actually do a regression here. The thing is, inside this app, it's not exactly connected to the rest of the features of the calculator. So we're going to actually do it inside the spreadsheet or the calculator page so we can define it and then operate on it. So what I have done is I've actually done a scatter plot of the same data. So I've put the data into a spreadsheet. So you can see here is my run 1 depth and my run 1 pressure. And then I'm going to do a scatter plot. So I've got a window set up here to do a scatter plot. So I'm going to say menu, graph entry edit. I'm going to go down to scatter plot. Okay, I'm going to tell it I want my horizontal axis to be depth. So I'm going to go run 1 depth. Tab down to my Y, hit my var key, tell it I want pressure there, and there it is. Now I don't like how it puts all this crap there, so I'm going to get rid of it. I'm going to hide it. Hide show the labels. Okay, so now I'm going to fit a curve to this thing, just to kind of see what it looks like. Now to fit a curve, I'm going to go into a calculator page that I can then use for the curve fit and then define the functions as I see fit. So let me add a calculator page to the mix here. Oops, accidentally hit the wrong thing. Let me go back and add a calculator page. There we go. And to do a curve fit, I'm going to go down to statistics. I'm going to go to stat calculations. And I've got 2 linear regression models. These are really doing the same thing. One is of the form mx plus b, because math people like mx plus b. The other one is a plus bx, because science people tend to like a plus bx. So it really doesn't matter which one you use. It's going to give you the same expression. I'm just going to use mx plus b, because after all, it's calculus class, right? So, all right, so I'm going to need to tell it what I want on the horizontal axis, which is what I just plotted. So I want depth on the horizontal axis. What I want for the y-axis, I'm going to say pressure. And it's going to store it in F2 for me, right? So you can see that F1 was already occupied by the function that I had plotted up here. So it just went to F2 as the next function registry. And there it is. You can see the expression. If you want to see what it looks like, we can actually go in and look at the graph of it. So if I double click here and I switch back to function plotter, and I go up, and there it is. It actually automatically stored it. This is why I got out of the DataQuest app and did all this within the spreadsheet and calculator and graphs page, because they're all dynamically linked. So it's a lot easier. Now when I hit enter, you'll see it show up. Swing, there it is. All right, so there's what our function looks like. Now I can use any variable name I want. I can call it, instead of f2 of x, I could call it f2 of d, however you like to do it. What I am going to do, just so that we gain some meaning from our notation that I've got here, is I'm going to go back over to the calculator page, and I'm just going to type in f2 of d, and what that's going to do is it's going to substitute all the x's with d's. Okay, and so you see the exact same function, except now it's got d's in it. And now I'm going to actually define this as p of d. So I'm going to say menu, action 1, I'm going to define p of d to be equal to, Now, I am going to make a slight adjustment here because the measurement that we had for pressure was actually in kilopascals. Since we're ultimately trying to convert everything into newtons, okay, I need to keep my units consistent. So what I'm going to do is I'm going to change it from kilopascals to pascals. So remember, 1 kilopascal is really 1,000 pascals. So I need to basically multiply this whole thing by 1,000. So what I'm going to do is I'm going to say 1,000 times the quantity, and I'm going to up and grab this kilopascal version of it, and that's going to convert all of my kilopascals to pascals. Looks like it's not quite high enough. Let me pull this up just a tad. Maybe see a little bit better. Oh, that's a little too big. Shrink it down just a bit. There we go. We'll be able to see the bottom of it, but not too much. Okay. There we go. All right. So now I'm going to define this guy. And there we have our pressure as a function of D in pascals instead of kilopascals. All right, now I want to keep in mind that my D here, let me slide this over just a little bit as I adjusted that. I ended up with a slightly different, what I have here. So this said D was 18.2 minus Y. Okay, there, now we can see it a little better. All right, so now here's what I'm going to do. I'm going to construct a product that's going to give my little strips of force based on my little strips of pressure and my little strips of area. Since I've got my area function and I've got my pressure function, I can put those guys all together. Right? So ultimately, I'm going to integrate. And again, I would like this in terms of y, so y is going to go from a y of 0 to a y of 18.2. So I'm going to go 0, 18.2. And now I'm going to put the pressure area combinations. So my pressure function is P of, and this is P of D, but I'm going to write it as P of 18.2 minus y, because we've defined it as P of D. And D is simply 18.2 minus y. Okay. Now I'm going to multiply by the area. So that's going to be this function here. Let me see. I can define it if I want. I can call this maybe the width of the strip, let's say. If I eliminate the delta y, it simply becomes the width of the strip. So let me do that, just so we can kind of see. Define w of y, make it a function of y, is equal to the fourth root of y divided by 0.000111375. Oops, and I need to double it because I've got twice the distance. Okay, so basically all I just did was I defined this guy here as w of y, width of the strip. Okay, when I multiply it by the delta y, the dy, it's going to give me the area of the strip. So I'm going to take the pressure times the width as a function of y times dy. So let's take a look at that. So let me integrate from 0 to 18.2. P of 18.2 minus y. Notice, by the way, if I plug 18.2 in for y here, I get P of 18.2 minus 18.2, which is P of 0, aka a depth of 0. That's at the very top. Okay, so all I'm doing is just shifting the location just a little bit. Okay, I'm going to then multiply that guy by the width as a function of y. Okay, we've created that function right here, the width part of the strip from here to here. And we're going to multiply by the thickness of the strip, which is dy. And what I get is, I get 9396555. I think 1, 2, 3. Yep, 4 5s. Let's say 0.8. Or there's no need to keep that many digits. Let's change this 5 to a 6. Okay. And my units here would be in newtons because I had converted to pascals instead of kilopascals. Okay, so right now, let me put some commas in here. 1, 2, 3. Okay. So this is giving me about 93 million newtons of force that we are placing on this dam total. Okay. So, but again, just like everything in Calc 2, we chop things up into tiny pieces and we add up the parts. And so that's what we're doing here. And this allows us to take varying pressures as well as varying areas of strips and put those together in a dynamically changing expression to be able to compute the total force. All right. Hope this is helpful, and I hope it helps in the write-up of the lab. Thanks.